We're going to start our work now solving systems of equation using power series. We're looking at a differential equation a2 of x y double prime plus a1 of x y prime plus a naught of x y is equal to 0. Second order differential equation, and the coefficient functions a2 of x, a1 of x, etc. indicate that we can expect up to a variable x in our coefficient functions. Standard form, as we've seen before, is y double prime plus p of x y prime plus q of x y is equal to 0. We start with a definition. A point x equals x naught is an ordinary point if p and q are analytic at x naught, meaning that power series representations exist centered around x equals x naught. A point that is not ordinary is singular. Singular points are going to be the focus of the next set of videos. This set focuses only on ordinary points. Another way to characterize what this says in the definition is x naught is an ordinary point if it doesn't make the a2 of x coefficient function equal to 0. We next see an important theorem about ordinary points. If x equals x naught is an ordinary point of the differential equation we saw above, then we can always find two linearly independent solutions of the form of a power series. The sum is y goes from n to infinity, c sub n, x minus x naught to the n. As I said before though, for us, x naught is equal to 0, which simplifies the form of the power series that we're going to end up writing down. Let's see what this looks like in an example. We have the differential equation y double prime plus 2x y prime plus 2y is equal to 0. We're going to find two power series solutions. We're told we're centering around the ordinary point x equals 0, as I said, and the flag that this is an ordinary point is just a reminder that x equals 0 does not zero out the y double prime term. Like we've done so many times in this course, we're going to write down a form of solution. In this case, y goes for n to infinity of c sub n x to the n, and then differentiate. You might remember that when we differentiate a series, the general term of which includes x to the n, the starting value for our index increases by 1 each time we differentiate. So y prime is the sum as n goes from 1 to infinity of n cn x to the n minus 1, and y double prime is the sum as n goes from 2 to infinity of n times n minus 1 c sub n x to the n minus 2 from repeated uses of the power rule for differentiation. I'll take this work in multiple steps, but in the future I might shorten them up. For y double prime, we have our n goes from 2 to infinity of n times n minus 1 c sub n x to the n minus 2. Next term is plus 2y prime, plus 2xy prime, and so plus 2x times the sum as n goes from 1 to infinity of n cn x to the n minus 1, plus 2y, so plus 2 times the sum as n goes from 0 to infinity of c sub n x to the n. And what we're working with is a differential equation, and so I really request that you maintain the form of an equation. It is actually incorrect if you don't. Now, as I said, I'm going to take this in multiple steps that I might shorten up as the series progresses, the series of videos progresses. So the first term doesn't have any change. What I need to do is deal with the second term and the 2 in the third term here. Having rewritten the first term, we'll note that the second term had a coefficient of 2, and one of the ways I don't lose track of that 2, or I try to prevent losing track of that 2, is putting it inside the sigma expression. And then we have x times x to the n minus 1 in this term. And you may remember that when we multiply numbers that have the same base, we add their exponents. So the second sigma expression is the sum as n goes from 1 to infinity of n cn x to the n, because the power of x has increased by 1. At this point, the only change I'm making to the third term is writing the 2 inside the sigma instead of leaving it outside where it's easy to lose track of. Now I want to make the exponents match, and then I want to make the indices match so I can combine what we're looking at into a single sigma expression. I will always do it in this order: exponents first, and then indices. I see two sigma expressions that have x to the n, and when we see x to the n minus 2, I'm kind of playing this out in my head here. I want to add 2 to that exponent to make the x to the n's all match. And if I add 2 to that exponent, I need to subtract 2 from the index to offset that. And if I were to do that and the index, the starting value for the index turned out to be negative, I wouldn't do it. I would adjust the other ones instead. I mean, it all works out to mean the same thing, but I just avoid negative starting values for indices. For the first sigma expression, the one in blue, the actual substitution that I'm going to make is that k is equal to n minus 2 so that n is equal to k plus 2. But I rarely think of it in those terms. I just want this to look like x to the k, and so what that's going to require is for me to add 2 everywhere and then change n to k. So we have the sum, I'll fill in the index in just a moment, but k plus 2, k plus 1, c sub k plus 2, x to the k. Now I said add 2 everywhere, and what I meant was inside the sigma expression. The index, we move in the opposite direction to offset. So here it looks like we added 2 everywhere. So for the starting value of the index, I'm going to subtract 2, and this is going to start at k equals 0, goes on to infinity. No changes need to be made for the second and third sigma expressions, except that n is going to be replaced by k. So let me just write those down. And then turn our attention to making the indices match now. In order to do that, I'm going to look at the indices that are smaller than any of the other indices that I see. We have k equals 0, k equals 1, k equals 0. If we write down the blue, the first k equals 0 term, and then the purple, the last k equals 0 term, then both of those would be sums that would start with k equals 1. So first writing down the blue k equals 0 term, we have 2c2. Writing down the k equals 0 term for the third sigma expression, the one that represented y, gives us 2c sub 0. And then for what we have left, everything starts now at k equals 1. Nothing else about any of the sigma expression changes. So let me just get these down. And now what we have are two terms, 2c2 plus 2c0, plus 3 sigma expressions, all of which have the same starting value, and they all feature x to the k. So we can combine those into a single sigma expression. We get the sum as k goes from 1 to infinity. I'm going to write down the x to the k outside of the entire thing. And then from the blue one, we have k plus 2, k plus 1, c sub k plus 2. From the green one, we have plus 2k c sub k. And from the purple one, we have plus 2c sub k. The whole thing is equal to 0. And this is the point where it's really important to understand the importance of the 0 on the right-hand side. What we're looking at is 2c2 plus 2c0. I had that as cn, but it should have been c0. That's a constant term on the left-hand side. Then when k equals 1 for the sigma expressions, x to the k would be an x term. When k is 2, that's an x squared term, and when k is 3, that's x cubed. You see how it goes. On the right-hand side, we have 0, and we might as well write that as 0 plus 0x plus 0x squared plus so on, right? All the terms are 0. So the constants on the left-hand side add up to 0 because the constant on the right-hand side is 0. That gives us the equation 2c2 plus 2c0 is equal to 0. And then all of the other coefficients of x are equal to 0 on the right-hand side, and we can write that all down in one fell swoop by writing down k plus 2 times k plus 1, c sub k plus 2, and then we see we can factor out a ck and a 2. So plus 2 k plus 1 c sub k equals 0 for all values of k, 1, 2, etc. This gives us our recurrence relation. And when we have an equation that looks like this with the c sub k's and then the k plus 1 and k plus 2, all that stuff, what I'm going to do every single time is solve for the constant that has the highest subscript. So here we've got c sub k plus 2 is equal to, you might notice that k plus 1 divides out. We know we're not dividing by 0 there because k starts at 1, so k plus 1 is 2. C sub k plus 2 is equal to negative 2 over k plus 2 times c sub k for values of k starting at 1, 2, 3, etc. The reason I always solve for the constant that has the highest subscript is because this is a recursive relationship. And if I know what c sub k is, then I can find out what c sub k plus 2 is through this formula. This formula is what we refer to as the recurrence relation. And as far as I'm concerned, if it doesn't have this k equals 1, 2, 3 from the summation that we had, then the recurrence relation is actually incomplete. Since we know that k starts at 1, let's start generating terms by plugging 1 in place of k. For k equals 1, we have c sub 3, because that's c sub k plus 2, is equal to negative 2 over 3 times c sub 1. I don't have any information about c sub 1, so we're just going to keep going here. K equals 2. That's going to be c sub 2 plus 2, so c sub 4 is equal to negative 2 over, that 2 plus 2 is again 4, c sub 2. But wait a minute. Up here we had 2c2 plus 2c0 is equal to 0. Again, solving for the constant that has the highest subscript, we have c2 is equal to negative c sub 0. Therefore, c4 is negative 1/2 times negative c sub 0, and so is 1/2 c sub 0. For k equals 3, we have c sub 5 is equal to negative 2 over 5 times c sub 3. But c sub 3 is negative 2/3 c1, and so c5 is 4/15 times c sub 1. I'd say what we have is enough to start writing down our solution. Writing down our solution is dependent on knowing that the power series solution will always have the form y equals c sub 0 plus c1x plus c2x squared plus c3x, I'm going to keep writing these down, cubed plus c4x to the fourth plus c5x to the fifth, and that's where I'll stop, but I'll put plus dot dot dot. It is an infinite series. So our solution is y equals c sub 0. I don't have any information about c sub 0, so I just have to write that down. I likewise still don't have any information about c sub 1, so I'll write down c sub 1x. But when we get to that c sub 2x squared, c sub 2 is negative c sub 0. So now our solution is y equals c0 plus c1x minus c0x squared. c3x cubed is actually negative 2/3 c1x cubed. c4x to the fourth is 1/2 c sub 0 x to the fourth. And c5x to the fifth is 4/15 c1 x to the fifth. And as before, plus dot dot dot. Now you may notice that in our solution that we just wrote down, a few terms have the constant c sub 0, and a few terms have the constant c sub 1. So that actually parses out our two solutions. We can write it down factoring, well, I guess combining the c sub 0 terms and then factoring out the c sub 0, we get c sub 0 times 1 minus x squared plus 1/2 x to the fourth, and that's an infinite series, so plus dot dot dot. And then clustering together the c1 terms and factoring out the c1 gives us c1 times the quantity of x plus, minus 2/3 x cubed plus 4/15 x to the fifth plus dot dot dot. We're used to seeing by the superposition principle y is equal to c1y1 plus c2y2. I'm going to relabel the constants because of what we have here and say y is c0y1 plus c1y2. And that tells us what our two solutions are. y1 is 1 minus x squared plus 1/2 x to the fourth, and so on. y2 is x minus 2/3 x cubed plus 4/15 x to the fifth, and so on. And these are our two power series solutions. Generally, I'm going to ask you for 3 terms per solution if possible.